Now, coming to the last part of the gas laws, that is the states of matter. So, we will start the critical temperature. Now, what is a critical temperature? You can see it on the screen. Critical temperature of a gas may be defined as that temperature above which it cannot be liquefied, howsoever high pressure may be applied on the gas. That means critical temperature is a temperature that is what you can say is that above which the gases cannot be liquefied. Got it? Generally, for the liquefaction of gases, what we know, the pressure should be high and the temperature should be low. So, if you are applying a pressure, got it, above the critical temperature, any sort of pressure, whatever the high pressure you apply, but you find that the gases does not get liquefied. All right. Now let me give you an example. Gases like ammonia, sulfur dioxide, HCl, carbon dioxide, etc., could be liquefied by any of the modes. All right. So any of the modes means either by application of pressure at room temperature or by cooling the gas at atmospheric pressure, at higher atmospheric pressure. Got it? Again I repeat, either we can liquefy the gas by application of pressure at room temperature or by cooling the gas at higher atmospheric pressure. At higher pressure we can say that. Now the effect of temperature on the liquefaction of gases is found to be very important. At as higher the temperature of the gas, more difficult it is to liquefy it, and higher is the pressure required. Alright, what I said, that is the effect of temperature on the liquefaction of gases is found to be very important. It is very important. It is, as the temperature increases, as higher the temperature of the gas, more difficult is to liquefy it. Definitely, because you have to apply more and more pressure, the higher pressure is required. Alright, if the critical temperature is higher, then definitely more and more pressure is being required. For example, let us say, for example, you are having a temperature of minus 50 degrees Celsius. So the pressure required, let us say 7 atm, let us say the pressure is required. Now when it is minus 30 degree, definitely you know minus 30 is greater than minus 50, then the pressure may be required, let us say, if I've said 7 atm, let us say double, 14 atm. Now if it is, let us say, minus 10 degree, let us say, alright, the pressure may be required, there is around 28. So you can see, what you find is that as the temperature goes on increasing, the pressure also increases. Got it? So for that reason, it's observed that gases like hydrogen, helium, oxygen, nitrogen, which are the non-polar gases, could not be liquefied at room temperature. Could not be liquefied at room temperature. Got it? By the application of pressure alone. Got it? So hence at one time these gases were called as a permanent gases, these non-polar gases, because it was thought that we cannot liquefy at all these particular gases. But now it is known that if you want to liquefy these gases, first you have to cool it down, you have to bring down the temperature, then if you increase the pressure, then only gases can be liquefied, so to say. So this particular temperature is known as a critical temperature. Now I hope you got it. What is critical temperature? So critical temperature for that reason defined as that temperature above which gases cannot be liquefied. Got it? As I said, you know, that nitrogen, oxygen, hydrogen, these gases were thought to be as permanent gases because these are the non-polar gases, and it was thought that we cannot liquefy it at all. It was thought that we cannot liquefy these gases at all, we can't liquefy it at all. So but now it is believed that no, by lowering the temperature, if you lower the temperature and then if you increase the pressure, then definitely we can liquefy these gases. So this particular temperature is called as a critical temperature. Got it? Now corresponding to that particular temperature, look at the screen, the pressure required to liquefy the gas at the critical temperature is called the critical pressure. So whatever the pressure is required, corresponding to the critical temperature, whatever the pressure is required to liquefy the gas is called as a critical pressure. The volume occupied by 1 mole of the gas at the critical temperature and the critical pressure is called the critical volume. Corresponding to the critical temperature and critical pressure, the volume which is occupied by the gas, it is called as the critical volume, which is represented by Tc, Pc and Vc. Tc is the critical temperature, Pc is the critical pressure, and Vc is the critical volume. Got it? So in this way, I think you got the idea what is critical temperature. We can say that. So critical temperature is very important. That is the critical temperature. Now, before going to the importance of critical temperature, let me just tell you the fluid which is a homogeneous mixture, which is called super critical fluid, also we call it as thus any fluid above its critical temperature and pressure is called as a supercritical fluid. Alright, what I said, the fluid which is a homogeneous mixture, alright, now is called as a supercritical fluid. Alright, the fluid is which is homogeneous mixture. Now any fluid above its critical temperature and pressure is called as a supercritical fluid, so to say. Alright, so idea you got it about the critical temperature. So critical temperature is very important to know, by which we can say we can cool the gases to a certain extent, and also we can apply the pressure also accordingly. Alright, accordingly, as I gave you them for some values, you can apply the pressure also accordingly. Alright, so intermolecular force of attraction can be increased either by increasing the pressure, alright, so that the molecules come close together, or by cooling the gas so that the kinetic energy of the molecules decreases and they come closer. Because ultimately what your aim is to bring the gas molecules closer to each other. Your aim is to increase the intermolecular forces among themselves. So you can increase the intermolecular forces either by increasing the pressure or by lowering the temperature. Alright, that we can do it. So thus gases can be liquefied by cooling or by application of pressure, or in certain cases you need both. Combined effect of both is required. Got it? Fine. So now next is we'll come to, that is the difference between gas and vapor. So substances above critical temperature is a gas, while below the critical temperature is a vapor. Alright, that's very important. You might have read it between what is a gas and what is a vapor. Like we say carbon dioxide is a gas, but we say water vapor. Alright, now speaking about carbon dioxide only, that is carbon dioxide below its critical temperature is called carbon dioxide vapor, and above critical temperature is called as a gas, because I said that is a substance above critical temperature is a gas. So carbon dioxide is a gas, but below critical temperature it is called as a carbon dioxide vapor. It is known as, okay. So now the importance of critical temperature was saying you, that is critical temperature of a gas is a measure of the strength of the intermolecular forces of attraction. Just now I said that is, if the intermolecular force of attraction is stronger, the gases can be easily liquefied by application of pressure. Alright, so weaker are the intermolecular forces, more difficult is to liquefy the gases. So in case of non-polar gases like hydrogen, oxygen, nitrogen, you find it out that the intermolecular force of attraction is weak. So hence it is very difficult to liquefy the gas. For that reason I said you just now that these gases were earlier known as permanent gases, because we were not able to liquefy these gases. But later on, as I said, we realized that no, by lowering the by lowering the temperature and by increasing the pressure, we will be able to liquefy these gases. Alright, so hence critical temperature is very important. That is, it gives the strength of the intermolecular force of attraction of the gases. Thus you find helium, hydrogen, nitrogen, oxygen, they have got weak intermolecular forces, they are difficult to liquefy and have low critical temperature. Alright, on the other hand, carbon dioxide and ammonia have strong intermolecular force of attraction. They can be easily liquefied and the critical temperature is also higher. Alright, the critical temperature is also high. Clear? Which is above room temperature, so to say, we can say that, which is above room temperature. Alright, and also we have discussed that Van der Waals constant A is also a measure of the intermolecular forces of attraction. Alright, so it is found that the values of the constant A increases in the same order as the critical temperature, we can say that, in the same order. So just an example I'll give you, that the critical temperature of helium is 5.2, hydrogen is 33.2, nitrogen is 126.2, carbon monoxide is 134. In this way, you not have to remember this. Don't think that I have to remember this. No, just I remember it, so I am saying you. Similarly, for helium, the value of A is that is Van der Waals constant is 0.0341. For hydrogen, it is 0.244. For nitrogen, it is 1.39. So it is increasing. What I say, that is Tc for helium is 5.2, for hydrogen is 33.2, nitrogen is 126.2. Similarly, A, that is Van der Waals constant A for helium is 0.0341, hydrogen is 0.244, nitrogen is 1.39. So what you find is increasing. or it is increasing. So as critical temperature increases, van der Waals constant also increases. We can say that accordingly, because van der Waals constant is also a measure of the intermolecular force of attraction between the gases. We can say that. So thus you may write down this one. The ease of liquefaction of some of the gases is in the order: SO2 is greater than Cl2 is greater than ammonia is greater than HCl is greater than CO2 is greater than CH4 is greater than CO is greater than N2 is greater than H2 is greater than He. Again I repeat, that is the ease of liquefaction of some of the gases is in the order. So SO2 can be easily liquefied. So SO2 is greater than Cl2. Cl2 can be easily liquefied than ammonia. Then ammonia is greater than HCl. HCl is greater than CO2. CO2 is greater than CH4. CH4 is greater than CO. CO is greater than N2. N2 is greater than H2. H2 is greater than He. Alright, so first you have seen that I have kept the polar gases, then I have kept the non-polar gases at the last. N2, H2, He is at the last. We can say that He is inert gas, never it will form any molecules. Never they will come closer to each other. So it has got highest critical temperature, we can say that, He, we can say. Alright, just now I said, 5.2 it is the critical temperature is clear. So in this way, this is about your critical temperature and the importance of critical temperature that I told you. Now next we will come to the liquid state. Alright, liquid state. So in the liquid states, you have read it in the lower classes that liquids is made up of molecules. The molecules of the liquid are quite close together. We can say that the intermolecular force of attraction in liquid are quite large, that is compared to gas, I should say. The molecules of a liquid are in a state of continuous rapid motion. We can say that. Alright, the molecules in liquid, they are always colliding with one another. Alright, we have read it in the Brownian motion also about it. And the average kinetic energy of the molecules of liquid is directly proportional to the absolute temperature. That we have read it in the kinetic theory of gases also, that the kinetic energy of a gas is directly proportional to the absolute temperature. So here also same thing, the average kinetic energy of the molecules of a liquid is directly proportional to the absolute temperature. Due to this reason, liquids, they have no definite shape. They take the shape of the container in which it is kept. They have a definite volume, of course, liquid. They have much higher density than that of gases, but lower than that of solids, and they are less compressible than gases. Liquids are less compressible in nature. Liquids diffuse like gases, but the diffusion in liquid is quite slow compared to that of gases. We can say that. Now, coming to some other properties of the liquids is that liquid exerts vapor pressure. Vapor pressure, we can say that. Now, what is vapor pressure? You can see it on the screen. Vapor pressure of liquid at any temperature may be defined as the pressure exerted by the vapor present above the liquid in equilibrium with the liquid at that temperature. Alright, it is exerted by the vapor present above the liquid in equilibrium with the liquid at that temperature. Now, what do you mean by that? Now, let us say you will take a particular container. Got it? A closed container. You take it. You take some water in it. You close the lid container with the help of a lid. You close it. Now you heat the liquid. After some time, the liquid will become hot and the water will become hot and it will vaporize. Alright. Now the water vapor, what you will find is that it is going to condense on the lid, on the cooler part of the container. We can say that the lid is a cooler part of the container. Lid means dhakkan. Alright, that's the cooler part of the container. The water vapor is going to condense because water vapor cannot escape, because I have taken a closed container. Now listen here carefully. What you will find, that the liquid condenses on the lid, that is on the cooler part of the container. So it exerts pressure downward. Alright. Now the vapor is going upward. It exerts pressure upward. Now when the two are in equilibrium with one another, that is the condensation pressure and the pressure exerted by the liquid, that is in the upward direction. Got it? So when the two are in equilibrium with one another, then the pressure which you are getting, that equilibrium pressure which you are getting it, that is known as the vapor pressure of the liquid at that particular temperature. Alright, what I said, that is when you are heating a particular liquid, any liquid, let us say water. So the water vapor comes up, it exerts pressure in the upward direction. Now this water vapor cannot escape. It gets condensed on the cooler part of the container. So the condensation pressure is downward. The water vapor is upward, condensation pressure is downward. Now when both the pressure are at equilibrium, alright, and that equilibrium pressure which is exerted, that is called as the vapor pressure of the liquid. So hence it is said that vapor pressure of liquid at any temperature, may be defined as the pressure exerted by the vapor present of the liquid in equilibrium with the liquid at that temperature. So it is an equilibrium. So it is an equilibrium pressure, so to say. Got it? So I hope you understood what is a vapor pressure. Got it? So now next is that is simply the condensation pressure and the pressure applied by the liquid in the upward direction when they are at equilibrium with each other. Then what you find is that that particular pressure is called as the vapor pressure. Now due to what you can say, due to the process of evaporation, evaporation, you know, it causes cooling. Got it? And definitely, like, how can we say that evaporation causes cooling? What we can see is that suppose you have come out, that is in the summer, let us say, or now also in this season also, suppose you have gone outside and you have come out from the outside, so you will find that you are sweating. Now if you sit under the fan, you will feel comfortable because sweat which will evaporate from your body, it takes away the heat from the body and you will feel cooler. Got it? You will feel cool. Relatively, you will feel cool. We can say that. So hence, we can say that evaporation causes cooling. Similarly, if you take some that is ether on your palm. Got it? If you take some ether means spirit. We can say that on your palm. Got it? So it causes, when it vaporizes the ether from your palm, it takes away the heat from the palm and it vaporizes. So it causes cooling. You feel a cooling effect. We can say that. Now, what are the factors which affects the vapor pressure? One is the nature of the liquid. So definitely, if the intermolecular force of attraction in the liquid are weak, if the intermolecular forces of attraction in the liquid are weak, the molecules can leave the liquid and come into the vapor phase. Got it? And hence the vapor pressure will be higher. That means I should say the liquids which are more volatile in nature exerts more vapor pressure than the liquids which are non-volatile in nature. For example, if you say alcohol and water. So alcohol is more volatile than water. So alcohol will exert more vapor pressure than water because the intermolecular force of attraction in this alcohol is weak. Got it? Compared to that of water. So alcohol vaporizes easily. Got it? It's a volatile liquid. Got it? Clear? So in this way, the liquid which are more volatile in nature exerts more vapor pressure compared to the liquid which are less volatile in nature. We can say that. Now, effect of temperature. Now, as the temperature of the liquid is increased, the vapor pressure of the liquid increases. Got it? As the vapor pressure, what you can say, temperature is increased, vapor pressure also increases. We can say that accordingly. So you will be studying more about it in class 12 in solution chapter. You will be studying in details about it. We will be studying a law also there, that is said to be as Rolle's law there, in details about it. Now we can say that only this much I can say you, that as the temperature of the liquid is increased, the vapor pressure of the liquid also increases. That means if you are heating a liquid at 50 degrees Celsius and if you heat another liquid at 70 degrees Celsius, then the liquid which is at 70 degrees Celsius exerts more vapor pressure than the liquid which is at 50 degrees Celsius, so to say. Got it? So in this way, the factors affecting vapor pressure is that one is the nature of the liquid. So volatile liquid exerts more vapor pressure than the less volatile liquid. And effect of temperature is that as the temperature increases, vapor pressure also increases. Got it? Now, coming to the boiling point of a liquid. So what is the boiling point? It is defined as the temperature at which the vapor pressure of the liquid becomes equal to the external pressure. Got it? Now, as I said you that when you get the vapor pressure of the liquid, now when the liquid vaporizes, when the vapor pressure and the atmospheric pressure is equal, then the liquid starts boiling and after that it starts vaporizing. So the temperature at which the liquid boils, that is called as the boiling point of the liquid. We can say that. The temperature which is the liquid boiling. Suppose if the liquid boils at normal atmospheric pressure, that is called as a normal boiling point of the liquid. Means when the external pressure is equal to the normal atmospheric pressure. Normal atmospheric pressure is 180 m or 760 mm. So that particular boiling point is called as a normal boiling point, so to say. Got it? And when the external pressure is equal to 1 bar, the boiling point is called as a standard boiling point of the liquid. Listen carefully. When the external pressure is equal to normal atmospheric pressure, that is 760 mm or 180 m, the boiling point is called as a normal boiling point. Normal. When the external pressure is equal to 1 bar, it is not 180 m, 1 bar, the boiling point is called as a standard boiling point of the liquid. That is called as standard boiling point. So that's the difference between normal boiling point and the standard boiling point. Got it? So obviously if the external pressure is higher, more heat will be required to make the vapor pressure equal to the external pressure, and hence higher will be the boiling point. That is why in hospitals, Surgical instruments are sterilized in autoclaves in which boiling point of water is raised by using a weight to cover the vent. We can say that is a application of the boiling point upon the external pressure. We can say that. So as the external pressure increases, boiling point also increases. So in hospitals, the surgical instruments are being heated in autoclave. Autoclave means it's the instrument in which the pressure increases, just like your pressure cooker. We can say that, similar to that. Clear? You might have seen it also in hospitals, a covered what you can say instrument. Generally it is kept near the sister's cabin or something like that. We can say that. So in this way it is being used. Now difference between the boiling and evaporation, it may be asked to you in exam. So boiling takes place at a particular temperature where the vapor pressure equals to atmospheric pressure, but evaporation takes place at all temperatures. Every time evaporation is taking place, but boiling takes place at a particular temperature, which is called as the boiling point of the liquid. Now during boiling it involves the formation of the bubbles of the vapor below the surface of the liquid, but evaporation takes place only from the surface of the liquid. So boiling is a complete phenomena, total phenomena, but evaporation is a surface phenomena. Always evaporation takes place from the surface. Now next, coming to the heat of vaporization, the amount of heat required to change 1 mole of liquid into its vapor at its boiling point is called as the heat of vaporization of the liquid. The amount of heat which is required to convert it into vapor, that is 1 mole of liquid into vapor, 1 mole of water into vapor. So that is called as a heat of vaporization of the liquid, so to say. So already we have discussed about the critical temperature. We have studied, you have seen it, that if the critical temperature is higher, then definitely that is lower, then definitely it can be turned into a volatile liquid easily, and it can be turned into vapor also easily. Now next is surface tension. Surface tension. Now what is surface tension? Now surface tension is a characteristic property of a liquid which arises due to the fact that the molecules of the liquid at the surface are in different situation than those inside the liquid. Got it? Definitely the molecules which are at the surface of the liquid, definitely they are different than the molecules which are inside the liquid. Now different means what? Got it? Let us say a molecule inside the liquid is a liquid. Suppose you have taken a container, let us say a beaker, you have taken it and you have taken some water. So some molecules are, a lot of molecules are there. Let us say some molecules are which is there inside the container. Got it? So the lying inside the liquid. So what you find is that a particular molecule, let us say a particular molecule is surrounded by a number of molecules. Got it? Inside the liquid, and it is being pulled equally in all directions. So the net force of attraction attracted is that it is zero upon that particular molecules which is lying inside the liquid, which is lying inside the liquid. I am talking to you. Number of molecules is surrounding that particular liquid, and these molecules pull that particular liquid molecule towards itself. So the net force of attraction is equally in all directions. So the net force of attraction acting on the molecule will be zero. A molecule is in the middle and it is being pulled by other molecules from, what you can say, from all the sides. So the net force which is acting on the molecule is zero. However, a molecule lying at the surface is attracted more by the molecules lying in the bulk of the liquid than by the molecules lying above it in the vapor phase. That means, what I mean to say, that the molecules which are at the surface, it is being pulled inside only. Got it? Then the molecules which is lying above the liquid also some molecules are there which is in the vapor phase, mind it, which is in the vapor state always. Got it? Clear? So thus a molecule lying at the surface experiences a net inward attraction, we can say that. Inward attraction which is lying on the surface. So as a result of this net inward pull of the molecules which is lying at the surface behaves as if it is a stretched membrane. The surface behaves, the surface feels a tension. Got it? So due to this property of the liquid, the surface experiences, as I said you, a net inward attraction. And this net inward attraction which is experienced by the liquids, which is the liquid molecules on the surface, is called the surface tension. Got it? Because I said you very clearly that the liquid molecules which is at the surface, it is being pulled inward, and the liquid molecules which is inside the liquid, it is the net force which is acting on a particular molecule is zero. Any molecule we can say that. The net force acting on a molecule is 0 because it is being pulled equally from all the directions. Got it? So hence surface tension is defined as the force acting at right angles to the surface along 1 centimeter length of the surface. Got it? And its unit for that reason is Newton per meter, or in SI and CGS system it is dyne per centimeter, we can say that. I hope you understood what is that is surface tension. Very simple, it is the force acting on the surface of a particular liquid, and the molecules which are present on the surface of the liquid, they experience a net inward force, and that particular, due to which the membrane of the liquid, got it, the layer of the liquid, the upper layer of the liquid is stretched, we can say that, and that particular force, that particular property is called as the surface tension of the liquid, we can say that. Clear? So in this way there are certain, what you can say, that is results related with the property of the surface tension. One is that the what you can say, the drop of liquid is spherical. Any drop of liquid, it's spherical, whereas water drop or any other drop of liquid is spherical. It is not cubical or rhombical or rectangular. No, it is spherical. Why? Because it is in the lowest energy. When the liquid is spherical, when a drop of liquid is spherical, got it, it is having minimum surface area, 4 pi r square, you know that. So it is having minimum surface area, and hence it is at the lowest energetic state. So surface tension tries to decrease the surface area of the liquid to the minimum, as we can say. Surface tension tries to decrease the surface area of the liquid to the minimum. So a drop of liquid is spherical because for a given volume a sphere has a minimum surface area. A sphere has a minimum surface area. For a given volume, a sphere has a minimum surface area. I said, that if the energy will be lowest when the surface area will be minimum. So a sphere has a minimum surface area, so its energy is lowest. So energy is low means stability will be more. So hence liquid drop, if it is spherical, it will be more stable in nature because it has got a minimum surface area. So surface tension, for that reason I said, tries to decrease the surface of the liquid to minimum. Got it? Now rise of liquid in a capillary tube is one of the application of this particular surface tension, we can say that, rise of liquid in a capillary tube. That is we are getting the concave meniscus of water and the convex meniscus of mercury in a glass tube. Got it? Why? That is when the liquid is rising in a capillary tube, so in case of water the meniscus is concave, and in case of mercury the meniscus is convex. Now why it is so? This is on the basis of cohesive and the adhesive forces. Now what is cohesive forces? The attractive forces exist between the molecules of the same kind, between the same substance, like water, that is cohesive. But suppose the force existing between two different kind of molecules, that is called adhesive. For example, for that reason in the market, the gum which is available, we also call it as adhesive, because we take that gum and we put it in a piece of paper and we put another paper, they stick to each other. So there is a force of attraction between the gum, that is adhesive, and the paper. So hence this particular kind of force is called adhesive forces. If you don't understand this, let us take a glass of water. You throw the water, you will find still some water droplet sticks to the surface of the glass. What is that? That is adhesive forces, it's said to be as. So adhesive forces between water and glass, got it, and or between mercury and glass, we can say that. So if you compare, then adhesive forces are stronger than cohesive forces. In case of water taken in a glass tube, adhesive forces are stronger than the cohesive forces. Got it? Again I repeat, in case of water taken in a glass tube, adhesive forces are stronger than the cohesive forces. For that purpose, water level is what you can say, has got a concave meniscus, whereas the reverse is true for mercury, and hence it has got a convex meniscus. So in case of mercury, what you find is that adhesive forces is weaker than the cohesive forces. Adhesive forces is weaker than the cohesive forces. So the meniscus is convex in nature, we can say that. Got it? So the surface tension also of a liquid generally decreases with increase of temperature. The surface tension of a liquid generally decreases with increase of temperature and becomes zero at the critical temperature, we can say that. Got it? This you need to remember. The decrease in surface tension with increase in temperature is obviously due to the fact that with increase of temperature, the kinetic energy of the molecules increases. and therefore the intermolecular attraction decreases. Alright, what I said you, that the surface tension of a liquid generally decreases with increase of temperature and becomes zero at critical temperature. Why do we say that? Because the decrease in surface tension with increase of temperature is obviously due to the fact that with the increase of temperature, the kinetic energy of the molecules increases and therefore the intermolecular attraction decreases. The next point is your viscosity. Viscosity is nothing but known as the fluid friction. The force of friction which one part of the liquid offers to another part of the liquid is called viscosity. We can say that. In one part of the liquid offers to another part, that is called as the viscosity of the liquid. Now, the force of friction, I said you already, in which one part of the liquid offers to another part. Like suppose a liquid is moving it is moving in a pipe, or suppose it is flowing in a pipe, or is flowing on the surface of the floor, we can say that. So there are different layers of the liquid are there. So due to which sometimes it flows freely, sometimes it does not flow freely, we can say. So the one part of the liquid offers an obstruction to the layer of the other part of the liquid, and this particular force of obstruction which is offered from one part to the other part is called as the viscosity of the liquid. Now more of it you will read in physics about it. Now coefficient of viscosity is defined as the force of friction required to maintain a velocity difference of 1 centimeter per second between two parallel layers. That means when 1 centimeter apart and each having an area of 1 square centimeter. 1 centimeter apart between two parallel layers, it should be 1 centimeter, each having an area of 1 square centimeter. That is called as the coefficient of viscosity. We can say that. Got it? Coefficient of viscosity, we can say that. So, coefficient of viscosity for that reason defined as a force of friction required to maintain a velocity difference of 1 centimeter per second between two parallel layers, which is 1 centimeter apart. We can say that. So, what we find, greater are the intermolecular forces, higher is the viscosity of the liquid. So, water for that reason has higher viscosity than methyl alcohol, because intermolecular forces in water is greater than that of methyl alcohol. Got it? Again I repeat, greater at the intermolecular forces, higher is the viscosity of the liquid. Thus, water has higher viscosity than methyl alcohol. Why? Because intermolecular force of attraction in water is greater than that in methyl alcohol. Why intermolecular force of attraction is greater? Because hydrogen bonding is there. Got it? Hydrogen bonding in water molecule, hydrogen bonding is there. Got it? And what you can say, in methyl alcohol you will be having also the hydrogen bonding. What is? The hydrogen bonding is there. Clear? And van der Waals forces are also there, that is which are strong enough to result into high viscosity of the liquid. But what we find is that in water also intermolecular hydrogen bonding, methyl alcohol also intermolecular hydrogen bonding, but the intermolecular hydrogen bonding and the van der Waals forces are stronger in water than in methyl alcohol, so to say. Got it? Now with the increase of temperature, I have said you the kinetic energy of the molecules of the liquid increases, which can overcome the intermolecular forces. Hence the liquid starts flowing faster for that reason. In other words, the viscosity of the liquid decreases with increase in temperature. When you increase the temperature, the kinetic energy of the molecules increases. Got it? And intermolecular forces decreases, due to which the viscosity also decreases with increase in temperature. Got it? So this is all about this particular chapter. Thank you.